if we were to design a quantum satellite mission, let's start to break this problem down. And how do we, select some of these highest order, design considerations and parameters from the system level? So I think the first order is choosing the orbit, right? Choosing the kind of coverage that the mission wants to support in terms of, terrestrial ground stations, or other kinds of links. So selecting the orbit, I think, is kind of the first order decision to make. And then deciding, what is this mission going to achieve? If it's to test out, space grade quantum hardware, that's great. If we want to support a certain application, such as a secure communications or a QKD application, selecting which kind of protocol we want. Does it rely on prepare and measure or entanglement? Multiplexing schemes will play an influence in that. So selecting the protocol is kind of the second order, and will really kind of determine the follow through of other trade-offs and design parameters there. And some of the other things we're going to talk about, Suparna, if you can mention the importance of kind of the link direction, right? We spoke about uplink and downlink, but also the wavelengths play a critical role here.
Yeah, absolutely. With those higher level design aspects in mind, let's move towards the next level, which is which uplink or downlink are we going to be selecting here? Are we going to go for C-band or the telecommunication band for the quantum link? Are we going to pick the 780 nanometer or the silicon band? These are some other hardware related and constraints that also depend on these higher level orbital selection and QKD configuration. Based on all of these, we can design the lower level aspects and design parameters regarding link direction and wavelengths. There are more to be discussed here. These are some samples that we have picked here so that we can give an example of how we can go about coming from the higher level design features to the more lower level design features and understanding the trade-offs between them.
So, starting with that challenge, I think is a great place to start thinking about some of these trade-offs in the selection of the orbit itself. So thinking about how beam wandering, wavefront distortion can really determine, what can we do at these different orbits. For low Earth orbit, the advantage with LEO is that we're much closer to Earth, so we're going to have higher rates of quantum communication. If it's for just qubit transmission or entanglement distribution, we're going to have higher rates just due to the distance. We have, lower beam divergence and, smaller telescope apertures to actually collect the signal. However, there are challenges with LEO as well. Just from a system standpoint, it has lower coverage, right? So doesn't have a large field of view for global coverage. So there are trade-offs there. Also, LEO will require much more rapid and responsive and kind of dynamic adjustments to the ground stations and also the hardware on the LEO satellite itself. Just given how fast the LEO satellites are traversing, the point of view from an optical ground station on Earth. So correcting for this kind of beam wandering is non-trivial. As we move further and further from Earth into medium Earth orbit and geostationary orbit, the advantages here are that we do have wider field of view to Earth, so we have wider coverage for supporting quantum communication. This has nice advantages in terms of just general availability and connectivity to a variety of ground stations on Earth. This also enables the inter-satellite communications. The satellite-to-satellite links that we mentioned will play a critical role in enabling this global quantum internet. With MEO and GEO, it's much easier tracking relative to LEO, and we can correct for beam wandering by tracking this counter-propagating signal. The downsides of MEO and GEO are that they're further from Earth, so we're going to have lower key rates, lower just general qubit transmission and entanglement distribution rates down to Earth. And these are larger, more costly satellites and telescopes that we're going to need to enable this. So this is how the atmospheric effects really play a role, not just in terms of signal integrity and mitigation, but also play a role in how we design the system, what orbit we select, and what the goals of the mission are. So moving on from that highest order kind of design consideration, the orbit, The next order is selecting the protocol, right? And most satellite missions, as Suparna went over, have been targeting quantum key distribution for the purposes of secure communications. There are a variety of QKD protocols, those that rely on single qubits and leverage superposition. These are called prepare and measure protocols. The advantage is here that you really only need to maintain kind of one link at a time. So there's a single line of sight. There's higher key rates. It's a more simple setup. However, from a security standpoint, there are trade-offs here. So the notions of trust in your secure communications network play a role here in how you select your protocol and what you want to demonstrate. If this is for scientific purposes or testing out space grade hardware, that's one thing. If you want to make an operational system and carry production traffic and sensitive data, you have to think about these security trade-offs as well. So when it comes to entanglement-based protocols, or sometimes called device-independent QKD, these have nicer security features and properties. You don't have to trust the satellite to the degree you need to for prepare and measure. However, with entanglement, it's more complex. We require simultaneous line of sight and visibility to a variety of ground stations, whether it's an uplink configuration where the satellite is doing this Bell state measurement, or if it's the downlink, which is shown on the left here. So this will certainly impact the final key rates that we're going to get, the entanglement generation rates. So more complex pointing, acquisition, and tracking systems and subsystems are needed both on the satellite and on the ground stations. And we'll dive into the kind of hardware in a little bit here. So now that we've spoken more about the atmospheric effects, beam wandering, wavefront distortions, etc., and how this impacts the selection of the orbit as well as the protocol we want to support, Suparna, it'd be great if you can walk us through sort of the next two orders of system design choices in terms of the link direction, right, uplink versus downlink, but also the wavelength selection, which plays a really important role in realizing these systems.
Absolutely. Thanks for describing the very evident trade-offs that we need to be considering going from satellite orbit selection and the protocol selection. We've often seen that a lot of missions rely on the LEO orbits so far for just because of lower divergence and higher key rates, like you were mentioning. And with that in mind, let's also dive into what kind of trade-offs we need to face when we come for selecting link direction. Before we go deeper into this, I would like to describe some of the metrics that we'll be calling upon to understand the trade-offs. And the first of them is a point ahead angle. This refers to the angle at which we want to be aligning or aiming the transmitter slightly ahead of the receiver's current position in order for the signal to reach the receiver at the right time with the right angle. So this is just coming from the fact that there is a finite time for the optical beam to travel from the transmitter to the receiver. Meanwhile, the satellite would have traversed a certain distance, and we need to correctly orient the transmitter in order for the beam to be received accurately with high efficiency at the receiver. And there is another metric that we want to consider, which is the isoplanetic angle. In this case, this refers to the separation of two optical beams in sky when you can still allow for good overlap of these beams in the atmosphere, so that any effects due to turbulence that is seen by one beam can be used to correct the effects of turbulence on the other beam. So for example, let's see this graphic. If we would use a downlink beacon laser coming from satellite to the optical ground station in order to correct for the turbulence seen by an uplink going from the ground station to the satellite, we want those two beams to have an overlap. However, if the point ahead angle is significantly larger than the isoplanetic angle, then it would be, then the case here would be that these two beams will not have a significant overlap in the atmosphere, making it harder to correct for some effects such as beam wandering. So with these metrics in mind, let's move to understand how the trade-offs in selection of the link direction comes about. In the case of downlink, there is a significant effect of wavefront distortion. And this can be understood again from the fact that it's mainly in the atmospheric 10 kilometer atmospheric region close to the optical ground station, where we would see effects of refractive index fluctuations, etc., coming about and changing the beam profile and distorting the wavefront. And that is pronounced as the beam coming from the satellite to the ground station is going to traverse the last 10 kilometers. So here, this wavefront distortion can in fact also be corrected using adaptive optics system. So that is an aspect that we can correct for currently fairly well. When we come to the uplink, however, it's primarily affected by beam wandering, and it is less susceptible to wavefront distortions. So let's understand the beam wandering section first. So if we have a tilt in the beam that's coming from the optical ground station, as the beam traverses longer and longer distances after experiencing this tilt, the spatial displacement of the beam is just too significant by the time it reaches the satellite. So this is an effect that needs to be definitely corrected for when we have an uplink going from optical ground station to the satellite, and it's an important aspect that is not very trivial to correct for, especially in the orbits, because as we talked about before, the point ahead angle here turns out to be significantly larger than the isoplanetic angle. So a downlink beacon cannot be easily used to correct for the uplink transmitted signal. However, the wavefront distortions here are less significant for an uplink topology. This is just because of the beam divergence. The speckle pattern within the beam also gets distributed over a larger area, and then there is less finer distortion within the beam as it becomes larger and larger in size. But with these in mind, we can also draw upon the missions that have been up there and are planned so far. A lot of them are using downlinks for the quantum channel, and few of them are also working towards technology and are planning for missions that use uplink. Let's next dive into the important metric wavelength, which we have to consider when it comes to optical beams, and what is the wavelength band we want to be operating at. Is it the telecommunication band, also known as the C band? Here we're specifically talking about the 1550 nanometer band, where we already have fiber optic networks that are in place. So it allows for easier interfacing with those networks if we work at that wavelength band. There is lowest fiber loss, so it just makes sense to try to move towards that wavelength band even for satellite to ground communication, so that eventually we can have efficient conversion from coupling from the free space satellite to ground link to the terrestrial telecommunication link. There's also the other wavelength band, which is silicon band, 750 nanometer band. This has some significant advantages just coming from the fact that there is good technology for single photon detection that is going to have lower size, weight, power, and cost constraints coming in. And the silicon detector support is one of the key features here. In addition, we want to be considering how much of a beam divergence will occur as the optical beam traverses through free space. It's well known that with smaller wavelengths, there is lower beam divergence, which means the beam is more focused, so there is higher efficiency collection at the receiver's end. So the silicon band is also supportive of this because it has a lower wavelength, and we can have much higher efficiency in collection as compared to the telecommunication band. There are, however, other aspects to consider here. One is atmospheric transmittance, solar radiation spectrum. So essentially the role of atmosphere and sources of noise. Both the telecommunication band and silicon band have good transmittance when it comes to the atmosphere's role here. However, it's interesting to note that there is higher solar radiation at the 810 nanometer band or 780 nanometer band because of the sun, and this solar radiation can creep in as a source of noise when one wants to be moving towards daytime operation for QKD. So if there is interest for daytime operation for QKD, it would be more suitable to move towards the telecommunication or 1550 band, which has lower sources of noise coming from solar radiation. We also want to consider all the available technologies. This includes both the detectors and the photon sources. We'll be talking about photon sources later, but let's dive a little bit deeper into the photon detection and how that has primarily influenced why we pick silicon band in most of the missions that are coming in and those that have been achieved so far. In the case of C-band or the telecommunication band, it is better to use the superconducting nanowire single photon detectors as compared to the avalanche photodiodes, just because of the difference in efficiency. The SNSPDs have much higher efficiency as compared to the in-gas pad that we mentioned here, and this is going to allow for higher efficiency of detection and eventually also higher key rates. However, this comes with the drawback that we will need to have cryogenic operation, and this will take up a lot of power. Size and weight constraints might not fit in to a satellite payload. So if we need to have a detector on the payload, it is more beneficial to go for the avalanche photodiodes that do not have these constraints of cryogenic cooling, etc. So when we come to the silicon avalanche photodiodes, these have very good efficiency as compared to the C-band operation, and they can also be operated at room temperature. They have lower dark count rates. So all of this put together, it's just much more beneficial to have silicon pad on a payload if one needs to be doing photon detection on the payload. So with this in mind, most of the missions that have been launched so far have tried to aim towards the silicon band. There are more that are also exploring the 1550 nanometer band, especially for downlink. It's suitable because you don't necessarily need a detector on the payload to do that. But as these technologies are maturing more, we can see how in future we might be able to move towards a lower swap constraint for maybe SNSPD. So Mike, I would really like to get some of your thoughts on how these lower level design parameters that we discussed so far play a role, and especially the wavelength side of things.
Yeah, absolutely. I mean, this is really, really helpful information to talk about and consider when it comes to wavelength and understanding what's available today in the technology. Wavelength selection, also link direction. They're very different properties for different wavelengths. So this may make a certain wavelength much more suitable for, say, satellite to satellite links versus a sat to ground link. So understanding these trade-offs is extremely important. Understanding the propagation effects with each of these, and relating that again back to real world constraints, like LEO satellites only have a certain amount of space, size, weight, and power that it can support. So understanding where the technology is at, what form factors do they support. But I do want to reiterate and emphasize what you just said, Suparna, which is that this is a changing field. The hardware is constantly maturing. In the silicon band, we have small form factor, very kind of low cost and mature technology. But as we move towards the C band, and eventually, again, we want to work towards this quantum internet. So we want to interoperate with the fiber networks eventually, and the C band is very promising for that. So I just wanted to reiterate that this is a changing field, and there are many advancements constantly in terms of the improving the efficiency of these C-band detectors, also the dark counts and the form factor and the cooling systems. So as the hardware technology matures and becomes more space grade, these need to be resistant to radiation, needs to be resistant to temperature fluctuations as the satellite is orbiting. Needs to be resistant to vibration, right, during the launch. So these real world effects all play a critical role in the hardware selection. So this is all, very, very great, insightful information to talk about as we're designing these systems.